All right, so my talk today is on pulsations and precision, why binary stars form the building blocks of astrophysics. So basically, I'm just going to try and convince you all today why binary stars are interesting and fun to research. Okay, so I have many hats. I work at Villanova and I also work for NASA. So NASA fund my summer months of research on heartbeat stars, but also on obtaining fundamental parameters for red giant stars in binary systems. So I also work on Phoebe, which is the physics of eclipsing binary software. So that's a binary software package. I'm from the UK, for those of you that don't know me. Some of you remember me from there. I'm also involved in TESS and Kepler, and there's soon to have first light LSST. So LSST, formerly the Large Synoptic Survey Telescope, now it's the Legacy Survey of Space and Time. It's a 10-year survey in Chile that will observe the southern sky or the whole southern sky every 3 nights. Okay, so today's talk, I'm going to be talking first about binary star systems, just an introduction to binary stars, then a brief introduction to Astro Seismology, calibrating Astro Seismology using binary star systems. I'm going to then talk about heartbeat stars, and then I'm going to give you a summary. All right, so we'll start with binary stars. So 50% or over 50% of all stars are in binary star systems. And this is the only direct way to obtain fundamental stellar parameters. We can use interferometry for stars that are resolved, but for unresolved stars, this is the only direct way. They come in many different flavors. And by that, I mean that we can look at lots of different stars in binary systems. So most stars you can find in binary systems. So we're not limited to which stars we can assess during you're looking at binary systems. They're important distance indicators. They enable the study of equal ages and equal chemical compositions, and they're a testbed for stellar evolutionary theory. So when we get a preferential line of sight such that we obtain eclipses when one star passes in front of the other, we get eclipsing binaries. So eclipsing binaries are great because they show us information about, for example, the temperature ratio. And then if you get a totally eclipsing binary, whereby one star goes completely inside the other or passes completely in front of the other, when they're undergoing eclipses, you can determine very precise information about the radii of those stars, and also the masses. So if you have a partial eclipse, which is this one at the top here, so here we have light curves from the Kepler satellite, and here we have phase light curves. If you have a partial eclipse like this one here, if you puff up the radius a little bit and change the inclination a little bit, you'll get a model that also fits the light curve. So you can get a lot of variation in the inclination and in the radius if you only have partial eclipses. So for precise work, it's very important that you have these total eclipses, these flat bottoms here, when the star is completely inside of the other star. Okay, so some of the interesting things that we know about binary stars is that while we say that approximately 50% of all stars are in binary star systems, this is not 50% across the board. So for smaller mass stars like K dwarfs and M dwarfs, we have a very low multiplicity fraction, so on the order of 20%. But when you get to higher mass systems, for example, O and B stars, we know that most, if not all, of these stars are actually in binary star systems. And so here on the bottom, you have the mass, and here on the y-axis, you have the multiplicity fraction. And so the red is a model by Arnoux, and then the black is a model by Wells, which goes through the observations. We also know that there are a lot of multiple systems out there, and an interesting fact about these multiple systems is that orbital periods, so binary stars with orbital periods of days of on the order of 3 to 7 days, something like, less than 7 days. Most of the objects are multiples, so that means that they have 3 or more components. And then for objects with orbital periods less than 3 days, essentially all of these objects are seen to be multiples, where Tocqueville found a 96% occurrence rate of 3 or more stars in systems where the inner binary has a period of 3 days or less. So just to give you an example of some of the work that I'm doing on binary stars, this is one of 4 objects that I'm modeling at the moment. So here on the left, you can see the light curve. We have time on the x-axis and the normalized flux on the y-axis. The black are the points, are the observation points, and the blue is the model. And then here on the right, you have the radial velocity with the residuals on the bottom. So the purpose of this work that I'm doing, this work has already been submitted, is to obtain very, very precise masses and radii of what we call benchmark systems. So these systems just can join a very small number on the order of hundreds of systems that have very, very precise masses and radii. And so when I'm fitting these masses and radii, I obtain posteriors of the fitted parameters, but I also obtain distributions. So these distributions are calculated parameters from the posteriors that I've obtained. So if I obtain, for example, posteriors in potential, in inclination, then I can use those parameters to determine the masses and the radii. And I output distributions so that I can determine very precisely the uncertainties that are associated with these parameters. And then I put these parameters, these stars on stellar isochrones. These are mesa isochrones, mist isochrones. And I can determine from that very precisely the ages of these stars. And so here, this star we anticipate is 3.3 gigayears. And so here is another example. And this one here, you can see from the envelope, this object has variations that show it has spots in the outer envelope. And this even more so. And so the reason that these spots are being modeled with the blue line is because I include Gaussian processes in my model. So the forward model would not usually include these deviations due to spots, but I apply Gaussian processes to model the noise and also to model the spots in the outer envelope so that I can obtain the parameters to the best of my ability. Okay, so that's just binary stars by themselves, but now I'm going to have a brief summary on Astro Seismology. So as most of you already know, Astro Seismology is akin to seismology, which is the study of earthquakes, where we have primary waves, which are the longitudinal waves, secondary waves, which are the transverse waves, and we use detectors on the surface of the Earth to assess how long it takes for these waves to pass through the Earth. And from that, we know that the center of the Earth it has an iron core, and then we have the different layers of the Earth. So akin to seismology, we have astroseismology, which is the study of pulsations, where we have, again, P modes, which are longitudinal modes, which pass through the convective regions of the star, as well as the radiative regions. And then we have G modes, which are the transverse modes. And we also use satellites instead of detectors on the surface of the Earth. Here we use satellites to detect small changes in the flux. So why do we study these stellar pulsations? So there are 2 reasons to study stellar pulsations. One is to understand why and how certain types of stars pulsate. And the other is to use pulsations to learn about the more general properties of stars. So I'm going to first look at the second point, but I actually consider pulsations from both of these angles. Okay, so to start off with, here is an HR diagram. And you can see 40 years ago, we only knew the stars that are pulsating, that are in blue, but now we have a much broader knowledge about the pulsating stars and the types of pulsating stars on the HR diagram. So today I'm just going to be discussing solar-like oscillations. So we have the blue here and this solar-like giants over here, and then also Delta Scuti Gamma Dor stars, which are here. Okay, so solar-like oscillations are stochastically excited oscillations that are in resonance with the stellar eigenfrequencies. The causes of they have only lifetimes on the order of 2 to 4 days, but they are really excited with different phases. And here you can see a simulation that shows oscillations on the stellar surface, and this is the 5-minute stellar oscillation, where the amplitude is exaggerated. So when we're trying to obtain fundamental parameters of stars, there are 2 important parameters when it comes to astroseismology. One of those is nu max, or the frequency of maximum power, and that is the maximum of the envelope. And here you can see the maximum of the envelope is a function of stellar size. So I'm showing you here power spectra of lots of different stars. And as you can see, the frequency of maximum power, nu max, changes. And this is also showing you the stars in order of size. So these are the larger stars down here, and these are the smaller stars up here. And it shows you how the frequency of maximum power changes as a function of the stellar radius. And then the other important consideration for astroseismology when you're obtaining fundamental parameters is the large separation. And so that's the separation between 2 different frequencies with the same L value, but N value different by 1. So the same number of surface nodes, that's L, but N value, the concentric nodes within the star differ by 1. So using these 2 parameters and the effective temperature, we can determine the masses and radii of solar-like oscillations to a very high precision. And this has been done for many thousands of stars on the HR diagram. So here you can see some of the results of astroseismology. So all of these stars have had their frequency of maximum power and the masses and radii determined. So for solar-like oscillators on the main sequence, the masses and radii can be determined to 5 and 10% accuracy. But for red giants, it's been found that the masses and radii can be determined to 10 and 15%. So this is going to give me a segue into calibrating astroseismology. So some of my work is aimed towards improving the astroseismology of red giants so that we can beat down those error bars. And how are we going to do this? We're going to do this using binary stars. Okay, so so far 14 objects have been modeled and published using binary stars to try and calibrate astroseismology of red giants. So using binary stars, we determine the masses and the radii with minimal assumptions. And part of my work is to continue this. And so far, we've identified an additional 18 objects in the Kepler and K2 datasets, which we're applying our methods to. So it's not all just so straightforward. Some of the concerns that have been raised with the currently available binary star models is that they don't always agree with each other. So these are 3 models of the same object by 3 different authors. And as you can see, when you just put those models side by side, the the models differ quite significantly, especially in the depth of the primary eclipse, but you can also see here there are some mismatches as well. And so those translate into the actual results of the masses and radii. So here you can see the masses and the radii given by the 3 different authors. And while there is overlap with the mass, there is no overlap with 1 sigma for the radius. So we do have our own issues in binary star modeling as well. And just as an aside, from Astro Seismology, we got a mass of 1.45, which is over here. That's not even on this chart. And a radius of 13.6, which is up here. So my work is to improve the results of binary stars by using a more homogeneous and advanced modeling methods, and also to try and model more objects so that we have a better grasp of the results. So here you can see this is a poster that one of my students made, one of my undergraduate summer students, where she modeled the same objects in order to see how her results compared. So she hasn't quite finished this project yet, but one thing that she did find when she was modeling the project, her name is Lexi, was that the radial velocities which we used from the paper do not match up with the light curve. And that is to say that this object is undergoing apsidal motion. And so that is something that has to be taken into account when modeling these objects. And that's something that wasn't taken into account by any of the authors modeling the objects previously. So there are a lot of intricacies in binary star modeling, all of which can lead to different values for masses and radii, and all of which need to be considered in detail. So not only am I looking to Kepler and K2 for these objects, but I'm also looking to TESS as well. So this is in a recent publication by Dan Huber. He showed the kind of solar-like oscillators that we can expect to obtain with TESS. So on the x-axis, we have the distance, and on the y-axis, we have the solar radius. So this just shows that we can expect to obtain stars with larger solar radii that are closer, but we should, but TESS is expected to yield 1,000 to 2,000 solar-like oscillators, which is 2 to 4 times the yield of Kepler. So because of that, we're hoping to obtain many binaries with solar-like oscillating components from TESS. So we already started looking into this, and this is the Sb9 Catalog Results. So we took the results from the Sb9 Catalog, which are known binary stars that are double-line spectroscopic binaries. And so this shows we took the parallaxes from Gaia and we determined the luminosities. And so from here, we were able to separate the main sequence stars on the Sb9 catalog with the red giant stars. And so looking at these red giant stars, we also were in the Sb9 catalog, they also have the eccentricities of these stars. So we took the orbital period as a function of the eccentricity, and then we looked at the distribution of these red giant stars. So right now we know this is the line that shows one sector, the length of one sector. And this over here is the line that shows the length of the continuous viewing zone of TESS. So any stars that fall on this side here that are in the continuous viewing zone should be good candidates for obtaining radii and masses of solar-like oscillating red giants. So my work now is to take all of these red giant stars that we have already obtained masses and radii for, and to improve the solar-like oscillating relations for red giants through calibrations with binary stars, so that we can improve these thousands of detections and beat down those error bars and get more accurate masses and radii for these thousands of stars. So now I'm going to talk to you a little bit about heartbeat stars. So so far I've been talking to you about using Astro Seismology and binarity together to determine fundamental parameters about stars. But now I'm going to talk a little bit about heartbeat stars. So looking at pulsations and really just trying to understand the pulsations themselves. And I say heartbeat stars, but I know Connie prefers eccentric binary systems. So these heartbeat stars, which are extreme eccentric binary systems, all show one thing, which is extreme periastron brightenings. So that is, at the time of closest approach, these stars have gravitational interactions which cause a deformation in the stellar shape. And this deformation causes a change in the surface area, which the change can be an increase or a decrease, depending on whether you're looking face on, for example, in this diagram, or if you're looking down the axes of the star. If you're looking along there, it can be a decrease in the surface area that you see. So far we've identified 172 of these objects in the Kepler and K2 samples, with an increasing number also being identified in TESS. And some of them show eclipses, like this one here, but many of them do not. So for example, here, this increase in the light is due to us seeing the distortion of the stellar surface. And then the dip is also because of the change in orientation that we're seeing. And some of these stars also show very interesting pulsations. And those interesting pulsations are called tidally induced pulsations or tidally excited pulsations. And they occur because of the forcing of the tide. So every time one star passes the other, it's like the star is being hit like a gong. And that star starts to pulsate as it goes around the orbit. And then again, when we get this tidal interaction between the two stars when they're close together, it's again like hitting the gong. And so the signature of these pulsations is that they have a precise number of pulsations per orbit. They have a precise number of cycles. So they have either 5 cycles specifically per orbit, or 10 or 20. And we can see that because here we have a phase folded diagram. And even though the diagram is phase folded, if we can still see the pulsations, we would not see them if they were not precise multiples of the orbital period, because there would be constructive interference and destructive interference. So these were first discussed by Cowling in 1941 and by Zahn in 1975. So they've been discussed extensively, and the idea was by Zahn that they would cause radiative damping and they would cause circularization of the orbit. So some of the things that we found about these objects is not just that the frequency is a precise number per orbital of the orbital frequency, but also the phases are often determined. The azimuthal order is often determined by the phase. So by looking at the phase, we can predict where the azimuthal order, which is the M value, which dictates how many of the nodal lines go through the poles. So by looking at the phases of these stars, we can determine whether the pulsations are M equals 0 or M equals 2. So essentially all of the tidally induced pulsations are L equals 2. And so here this enables us to determine whether they're M equals 0 or M equals 2 as well, just by looking at the phases in relation to the angle of closest approach, the time of closest approach in the orbit. Okay, so here's one star that I have modeled, and this is called KIC 8164262. It's a very interesting object because it has very strong tidally induced pulsations. So the amplitude is on the order of a millimagnitude, and it pulsates 229 times per orbit very precisely. So here you can see the Fourier transform, And on the x-axis, we have frequency and in cycles per day. And on the y-axis, we have parts per million. And you can see that the 229th harmonic is on the order of a millimagnitude. And then look, if you can see this, the change in scale, any other peaks are significantly reduced, where we see two peaks due to rotation and then several other pulsations. So the idea for this very large peak is that it's caused due to a mechanism called resonant locking. So the idea is that if it wasn't for resonant locking, that pulsations would pass through resonance due to the orbit evolving. So as I said, the orbit is circularizing, the period of the orbit is changing, and also the evolution of the stars. So the internal eigenfrequencies of the stars are changing. And so the idea is that because of these two occurrences, that the pulsations would pass through resonance. But what actually happens in some cases, or what we're suggesting happens, is that these pulsations get locked into resonance because the orbital changes occur on the same time scales that the stellar eigenfrequencies change due to the evolution of the star itself, and through this locking mechanism occurs that keeps the pulsations in these high resonances for extended periods of time, and this speeds up the circularization of the orbit. So here we have on the x-axis we have the pulsation frequency in terms of the multiple of the orbital frequency, and then we have the amplitude of the frequency. And so here we show predictions. The dots show the predictions for where we would expect the non-resonantly locked pulsations to be, so just the tidally induced pulsations. And then here in the red blocks are the actually observed tidally induced pulsations. And then the dark green and the light green predictions show the tidally the predictions for the tidally locked pulsations for m=1 and m=2 modes. And so here we can see that this very high amplitude mode is a very good candidate for a resonantly locked mode. And again, this mechanism is predicted to increase the circularization rate. And for this star, it's suggested that it increases it by 500 times. So this star will circularize 500 times faster, at a rate 500 times faster than if this mode was not resonantly locked. And so more recently, we have started to look for more of these objects, and we found this was a study by Cheng et al. And we found in the study, when we assessed 3 different objects, we found one. It's not as strong a candidate, but as you can see, the one high frequency, high amplitude pulsation is close to overlapping the m=0 resonantly locked predictions. And so where do we look for these stars? So the next step that I'm taking with these stars is to look for more of these resonantly locked stars with resonantly locked modes. And so this figure shows you on the x-axis is period and on the y-axis is eccentricity. And this is a plot that shows all the eclipsing binaries that in the Kepler eclipsing binary catalog. And it shows you the distribution as a function of eccentricity. So as you can see here, there are a dearth of objects which have low periods and high eccentricities, where in this red box, we see objects that are undergoing circularization, because you can see that most of them are down here with very low eccentricities. And then in the blue box, you can see that there are no objects found except for this one red object, which is 8164262, the one that I showed you with the resonantly locked mode. And then down here in the green box, there's just a low rate of circularization, because these objects do not have, they don't get very close to each other at their time of closest approach. And so because of that, the circularization mechanisms are very slow. So what I'm doing with this is I'm looking at all these objects where we expect the tidal influences to be causing circularization. So in this outer envelope here, and also here where we can see that circularization is very active. So I'm looking at all of these objects and searching for objects with resonantly excited pulsations. And just for any of you that remember me from my master's thesis time, this object here is KIC 4544587, and that's my master's thesis star that shows tidally excited pulsations. Okay, so what we've learned about heartbeat stars is that they have tidally induced pulsations that are observationally linked with circularization, and that they undergo resonant locking. And so what we want to do now is create more evidence for resonant locking so that we can understand circularization in binary stars better. Okay, so to summarize and for future work, currently for red giant binaries, the Astro Seismology, so red giant stars, the Astro Seismology isn't as accurate as we would like, but binary stars can help. So through Kepler and TESS, I plan to work to provide a more robust and larger sample of benchmark systems with which to calibrate the Astro Seismology. And this should lead to an improved accuracy on the masses and radii for thousands of stars. And then for heartbeat stars, we know that heartbeat stars can be locked in configurations which keep their pulsations in resonance, and that speeds up the circularization. And by learning more about these resonant pulsations, we're going to learn more about the tidal evolution of binary stars. And with that, I'll say thank you, everybody, and that's the end of my talk.
Thank you very much, Kelly. Very nice talk. Beautiful data sets, amazing. Yeah. So if anyone has any questions, please tell so in the chat, and I will call your name, giving priority to the younger people first. Everyone is still in awe of the data sets, I think. Please, Dominic.
Hi, Kelly.
Hi, Dom.
How are you doing?
Good. Nice to see you.
Yes, we'll catch up afterwards. Okay, so my question, I actually have two questions. What's the eccentricity range that you can get this heartbeat phenomenon in? What's the sort of lower end where it's actually possible, given all the other combinations of parameters?
So it really depends on what you're talking about. So I know you were doing the one-sided pulsators, right? But so I mean, anything can really trigger tidally excited pulsations. Any low amount of eccentricity. For the tidally for the periastron variation. So that wiggle that you see in the closest approach. You see it more and more as the stars become more eccentric. But again, even if you have an eclipsing system, you can see it with a very small amount of eccentricity. So really, I guess it just depends on the definition of heartbeat stars, which there really isn't a clear definition for that.
Okay, that's interesting. And coupled to that, is there a sort of upper mass limit? Because I know some of us in the audience have been finding what I'll call morphologically things that look like heartbeat signatures in more massive stars and like the O stars, but they turn out maybe not to be heartbeat signatures. So because of the nature of the orbital periods of more massive stars, can we put an upper mass limit on heartbeat stars, or is that something that can't really be done?
So I don't think so. I don't see why we couldn't get massive stars in heartbeat stars. I don't see a reason. The reason that we haven't seen many so far as I'm aware, is because Kepler was limited to the lower end of the mass range. So we didn't have a lot of more massive stars with Kepler, so we just didn't see them. But I really don't see why there would be an upper mass limit.
Okay, that's great. Thanks very much.
But I'm interested, Dominic, why you said you don't think that those stars are heartbeat stars? Do you think there's something else?
There's a, well, maybe if Toma's in the call, I don't have everyone's list in front of me, but it's a system that Toma's been working on. It's two massive stars. And is he there? I heard someone speak.
Yeah, that's right.
Yeah, I am there, but my reception isn't good, so you better present it. You know the details better than I do.
That's certainly not true. Yeah, so there's two massive stars in a I think it's 80-ish days, if I've got the number right, period. And they have in the light curve, they have a feature which looks very much like the heartbeat. But when we asked Bert Pablo to model it, the masses and the radii that you need within Phoebe didn't make much sense, because the stars would have incredibly large radii. So in the end, the system appears to be undergoing a wind eclipse, which is a combination of an eclipse and excess light from the collision zone, and that gives you this sort of heartbeat-like system. But maybe I can show you some figures in the coffee break afterwards. It's quite an interesting system.
Yeah, I'd love to see it.
Okay, thank you. Then we have a question or two from Cool.
Hi, Kelly. Thank you very much.
Hi.
About the Kick 816 or 8, whatever that was, I noticed that the very high amplitude peak seemed to have a window function about it. Is that observational, or is that like caused by, or was it continuously viewed, or are there missing sectors?
I don't think there are missing sectors.
Are those, what are those peaks split by?
Let me see. Let me try and pull it up for you. Okay. Let's see. So after that, right, here we go. Can you see this?
No.
Oh, okay, let me try again. There we go.
You're still not sharing. Oh, there we
Yeah,
go.
yeah,
Okay.
there we go.
Okay.
These here.
Yes.
Yeah, that is window function, because as you can see, when we remove the peak, they go along with it. So that's window function.
Okay, that's pure window function. That makes me feel a little bit better. Otherwise, I was very confused as to what could have given rise to these things. But then the second question is with the resonant locking. Is that what's is like the rapid circularization what's driving the apsidal motion in this case, or does it have a component to what's driving it?
So I don't think that this one has very strong apsidal motion, but it's circularizing. So those are two different things. So it's just the circularization of the orbit itself rather than the rotation of the orbit. So tidally excited pulsations themselves take energy out of the orbit. So that drives the circularization. But this very high amplitude tidally excited pulsation is taking a large amount of energy because it's in resonance. So it's taking a lot of energy out of the orbit. And because it's locked in this resonance, it's going to be doing that for an extensive period of time. So it's causing a more rapid circularization of the orbit.
But wouldn't that naturally cause like an apparent change of the argument of periastron? Maybe not in an overall geometry term, but just because the orbit is in fact shrinking, when you see the eclipses will change over time.
I mean, there will be some exchange in angular momentum, but the circularization is just the condensing of the orbit.
Okay. All right, thank you.
Okay, thank you. And then we also have a question from Andrew.
Oh, indeed. I'm not too old for that. That's nice. Hi, Kelly. Thanks.
Hi, Andrew.
And I actually managed to find my video button here on the screen. Yeah, I'll have a couple of questions as well. And the first one will be rather technical about the system that you showed that was modeled by 3 different groups, and where you said that we have our own issues in binary modeling, and that the three models disagree. But is this really the issue with the binary model in itself, or is it an issue with the input light curve that perhaps was produced and processed differently by the three groups?
So actually both. I believe the detrending of the light curve plays a significant role, but also the program used by the groups, JKT-EBOP, doesn't include the physics that govern this part of the orbit. So it's a combination of not using the right software for the particular light curve and also the detrending. They all had their own methods for detrending, which is why I think Gaussian processes is the way forward to go for this, because it models the trends in the light curve rather than trying to fit, say, a polynomial to the light curve.
Yeah, thank you. And the second question is a more general one. When you say several times in your talk that you wanna better calibrate astroseismic models, Astro Seismology of red giants. So could you elaborate a bit further on what you exactly mean by that? Is this astroseismic models themselves that, you know, we know they're failing because people have to introduce this funky surface effect to actually get the frequency fitted? Or is it more about the evolutionary models that might be not so well calibrated in terms of stellar mass?
So my side of things is more presenting the masses and radii and the differences so that the calibration can occur. I mean, I know there have been different kinds of calibrations already applied, some more successful than others, but if we increase our data set of observed objects where we have the masses and radii from binarity, then we're going to be able to test the already available calibrations and then, if necessary, adjust them or update the calibrations themselves.
Yeah, okay, thank you.
Okay, thank you. Is anyone else has a question? If not, then I would like to thank Kelly again. Thank you very much, especially because you had to get up so early. It's early in the morning now where you live. So I think we need to give you a break now to catch your breath, and then I will give the floor again to Matthias, who will lead the coffee break afterwards.